I actually don't speak Spanish. My name is Brian. I hope you guys have had a good time at Ekoparty so far. Today I'm going to talk to you about leveraging model-specific registers for fun and for profit. Lame title, I know. My email address is here. It's RPM, stands for rotations per minute or rolos per mouth, at jhu.edu. And you'll notice my name is also in Korean. I'm moving to Seoul in 3 days, so if any of you come to South Korea, I don't know anybody, so please look me up, and we'll hack together. Let's go to it. So I've also, just so you know, I've brought some advanced hardware here from about 1999 to hack on, so I hope you guys are impressed with this very sophisticated machinery we will demo on our stuff today. Real quick, this is my About Me slide, just so you know who I am, what I do. I'm not hardcore. We at iSight like to do Occam's razor, which is essentially keep it simple, stupid, which is when you're thinking about how to implement something or when you're designing something, don't put in components that complicate things, just do shit really easily. And that's kind of the focus of this talk, is to go into use what you have available and hack with that and make it easier for yourself. Like think about what you have and what you can do with it. That's essentially how we hack at iSight, is just think about in interesting ways what you have and then what you can do with it. That's the whole idea of this talk. I essentially only have 1 year messing with Windows kernel, and it's the older version of the kernel. I only hack on Windows XP still, which is really lame. I know Windows 8 is coming out, you guys are all reversing that, the beta's out, yada yada yada, we'll talk about that. But I only had experience in the Windows kernel for 1 year, and previous to that, working on a ton of userland, malware, anti-RE, anti-RE, all that kind of stuff. So I'm no expert by any means, but today we're going to talk about some kernel stuff, some hardware stuff, which you guys are probably all way more experienced than I am. So feel free to, if we can, any questions or yell out or throw shmoo balls if I'm sucking, please do that. So today we're going to talk about model-specific registers. And specifically, model-specific registers are used to provide access to features that are generally tied to implementation-dependent aspects of a particular processor. And in particular, today I brought a NetBurst processor, which, if you guys don't know, is the P4 single core. It's very easy to program. Single core processors. There's not a lot of contention. There's not a lot of issues. It's old school, but it's easier. It was easier for me to get into the model-specific registers on Pentium 4. And just a little background, if you guys are interested, I'm not going to talk about the history of model-specific registers, but they were introduced, as far as I know, correct me if I'm wrong, on the Pentium, and Intel has been improving and adding to the functionality ever since. But that doesn't mean other processors don't support it. For instance, AMD's processors also have model-specific registers. I think Spark processors also have MSRs. I don't have any Sun boxes anymore, so I haven't been able to test this. You guys, I'm sure there's model-specific registers on other processors, but today it's all about the Pentiums, baby. So that's what we're going to talk about. So what specifically are model-specific registers? You guys might have read uninformed articles or other hacking articles about, hijacking model-specific registers or using stuff, blah, blah, blah. But they serve many purposes. Performance monitoring is one of the big ones, precise timing. Intel has something called PEBS, P-E-B-S, it's precise event-based sampling, I forget, but it's for performance monitoring. Debugging is also a big one, which is what I'm going to be focusing on today, and just ripping that apart. That's what we use entirely. So for instance, they provide program execution tracing indirectly through hardware, which we'll talk about. You can also tweak the functionality of the processor specifically with model-specific registers. So if you write to a register that, say, is in charge of the hardware prefetcher, you can turn it on and off. You can turn on and off thermal monitoring. So if you want to overclock your CPU, you just turn off the thermal monitor MSR, and then you'll get no alarms and no hardware shutdown stuff if it overheats. But you're okay with that because you're a hardware hacker guy. So there's lots you can do with MSRs. So there's a lot of cool playgrounds to mess around depending on what you're interested in. And as a side note, I mentioned that MSRs do a lot of debugging things, a lot of debugging functionality. which we're taking advantage of today. But in the past, you guys have probably been aware of yourselves or have read about people leveraging debugging functionality left in programs. I have some examples here, like HD Moore's VxWorks, the Wind River's embedded OS. They left the WDB agent stuff enabled. I think cable modems or modems have this embedded OS, and you could leverage the fact that they left this agent on there to gain root on these boxes, which is awesome. Another example, a lot of embedded devices, like some smart meters or some other interesting devices let you peek and poke in memory. So the embedded OS developers will leave functions to write to memory or to read memory. So you can essentially dump firmware from a lot of these devices that have this JTAG peek poke functionality left in on hardware. Another example of debugging stuff left in, Skype. When you use Skype on your computer, I actually have it running right now on mine, they have an option to turn on debug logs, and they're encrypted, but if you hack the client, you can get it to just decrypt the whole Skype log, and it's awesome because it has everybody you talk to that has their NAT address, their internal NAT and their external NAT IP addresses. So you can just talk to anybody on Skype, and the debug log leaks their IP addresses. And this is public knowledge. It's nothing new. This is just a list of things that were left around to play with. So again, going on the Occam's razor idea, if you leave debugging artifacts intact in the software, let's use those and let's play with them and let's do it. So there's so many more examples of the debugging artifacts left in modern and released software. So jumping right into it, if you have a processor you're using, again, I have Intel, I have a Netverse T4 Intel chip in this box. How I use it in the x86 instruction set is with these two instructions, essentially write MSR and read MSR. And in real mode, you need a current privilege level of 0, which means you need to have the highest privilege to even use these instructions, And in virtual 8086 mode, if you try to call these two instructions, you'll get a general protection fault. And in a virtual machine monitor, in non-root mode of a VMM, it's questionable if you can call them or not, depending on the security you set up in the virtual machine monitor itself. So this is just if you haven't heard of these instructions, here they are. I'm not going to actually tell you how to actually call them or what registers are used to pass information to them. You guys can look that up. So there's a shitload of MSRs. There's a ton of these awesome features to turn on and off, play with, etc. And how do you know what they are? Intel has loads of documentation describing the MSRs that they use in their instruction sets. AMD, not so much, but it's tough because Intel doesn't come out and say, here's all the MSRs, here's how they've changed, here's the address space we'll use for certain MSRs. So a lot of people have done work just brute forcing, just essentially trying to read and write just every single value from 0 to so that's probably not the best way. You can also check. There's another instruction you can call CPU ID, and it will write values into registers. You can then check yourself to see if certain MSRs are available for you to use. And this is better described in Intel documentation. I kind of wanted to just go through this with you so you know that there's ways you can find out what MSRs the processor you use in your machine has available to it. So access in Windows. So I use Windows a lot. I make money in Windows. I'm sure you guys all can imagine. Windows is the shit. So to access MSRs from CPL, current privilege level 3, ring 3, userland, whatever you guys want to call it, there's certain ways that you can do that without having to actually use those instructions from the kernel. So before I did this work, I wasn't actually a kernel expert. It's kind of foreign to me. So I prefer to use these APIs to read and write the MSRs. So in Windows XP, you need SE debug privilege, which is essentially root, to be able to call NT system debug control with the proper arguments to write to an MSR or read an MSR. And that technique was published by Alex sorry for butchering your name, in like 2006, so that's very old. Windows 7, you can use KD System Debug Control, which is obviously a kernel API, but if you boot into debug mode, you have SE debug privilege, and you have WinDebug installed. You can actually use this device that WinDebug creates, and you can send it the apples directly if you have the privileges from userland. You can read and write MSRs. That's kind of cool. So Windows 8, I got an email a couple days ago from Matt Sweesh, some French dude, he's awesome. He was reversing the kernel, and they have support to write to multiple MSRs, given that Windows 8 has the hypervisor or Hyper-V stuff built into it. So there's support, API level support in the kernel to read and write to MSRs. But it's my guess or my speculation that they're only going to allow certain MSRs to be read and written to. Using the sysenter and sysexit stuff, it requires certain MSRs. So I'm assuming that it's a restricted set you can use in Windows 8. Or it's going to be configured at a different level which MSRs you can read and write to, which we'll talk about. In Linux, if you guys use Linux, I hate Linux, it's cool, it's open source, etc., but I don't use it personally. I don't make money in Linux. There's a device mapped per CPU you can just read from, and write to. This is nothing new. This is just going over common stuff. So previous abuse of the processor available MSRs. Certain drivers in Windows were released in major products, like Norton Antivirus, for instance, had a driver that allowed you to call an ioctl that essentially let you read and write to any MSR without permissions, which is great because, as you can see down in the next bullet, you can hijack this MSR IA32 sysenter EIP. So when there's a sysexit, it needs to know where to go, and you can pretty much redirect, when it changes privileges, you can redirect what code is called. So if a driver provides access to read and write MSR, that's very bad, and that's actually happened multiple times in the past. The last two bullets here, you can use these MSRs to leak the base of the kernel in memory. If for some reason you are able to execute code and you need to find the base of the kernel, you can use this address that's stored in that MSR to help you. There's an uninformed article written by Escape, and BugCheck, I believe, that talks about that in 2007. You can also do system call hooking through this MSR called IA32 L star. I'm not going to get into these techniques specifically, but that essentially allows you to hijack the way Windows does system calls. So every time a system call is made, you can hijack the code that then calls the system call. So it's kind of like a detours type like hooking capability. Obviously, all these techniques require you to be obviously root in Windows to do. So still not that cool. So today, what we're going to talk about today, what am I going to tell you guys that's new, cool, why I'm actually here? So I'm going to do two things today. I'm going to give you yet another red pill. You've heard Joanna Rotanaska's talks. You've heard all these people talk about how to detect code in a virtualized environment. I'm going to give you yet another instruction you can use to detect if you're running in a VM or in an emulated environment. Not that cool. There's so many different ways to do this now. It's just something I thought of last minute. And we're also going to talk about how to do tracing stealthily with MSRs without modifying the binary you're trying to trace. But through my technique, I'll tell you today, you don't get disassembly. So there's no disassembly you get with this trace. It's just the linear address that the code took as it executed. And at best, you might be able to get the instruction values at each jump, but you're not going to be able to get the full disassembly listing. But it's fucking fast. It's really fast. Faster than anything else I've seen published. Also, I have a side note. I don't know why that's bouncing. Really annoying. There's a side note here. I just wanted to say this to everybody in the community. The sandbox I've seen that people run there, like all the analysts at all these companies run malware and sandboxes, and they use these shitty detours techniques. They hook the APIs, or they think they get fancy and they use push grant, right, instead of other like call or like a short call or something. And it's really funny because the stuff we see now just overwrites the instructions that are detoured, so your code isn't even called. So this is just a funny side. So the reason why the red pill stuff is interesting to me is because there's a lot of the anti-virtual machine code out there running around right now. A lot of the malware does pretty primitive checks to see if it's running in a VM. You see, blog posts about people reporting malware that they check the physical name of the disk to see if it says VMware on it, or they check, if your program files folder has in Windows, of course, if your program files folder has a folder named VMware or VMware tools or something. So the malware that we see that's using the host to monetize or to make money, it's using these VM detection techniques because most analysts that I know, they just run a piece of malware in a out-of-the-box virtual machine environment. I mean, you have these people that just run it in VMware and they have some tools running in the host, like some analysis code that will run inside the guest as well, and then it'll just say, okay, this is of this family, it did this to the disk, it did this. This is very common runtime analysis of malware in the VM. But again, the malware we're seeing is checking more and more hardcore if it's running in the VM or not. So it's interesting to me to say, how can I easily check it on the VM to pretty much screw everybody that's doing the analysis of malware? Because if I can reliably detect if I'm in a virtual environment, I can just run different code if I'm malicious and not run my actual payload. I can just do I'm poison ivy versus I'm actually a really interesting payload that has a 0 day. So you can do a lot of cool stuff if you think about it. Your targets that are interested in, that you're gonna the interesting people who you'll steal money from, they don't actually run VMs, right? They're running Windows XP on hardware, similar to this box here. So I think it's cool to throw another red pill technique for you guys to look at, figure out how to break it. So this is actually it. This is all you need to do. I left out some code intentionally here for the interested reader. So if you use this code and you read from that MSR, right, the value returned, if it's not 0, you're in a VM, essentially. And this code actually tested it on all of these, essentially these emulators and these virtual machines don't support reading from that MSR at all, because they don't know how to emulate it, or they don't know how to virtualize that MSR, and it's not supported, right? But if you run it on a actual machine, it will return 0, whereas these guys will return an error saying they don't know how to respond, they don't know what that MSR is. So it's a stupid way currently to detect in one instruction / couple instructions to check the return value if you're running in a virtual machine. So there's one simple extension of this. So there's also another interesting thing. Intel has something called VMX, I'm sure you guys have all heard of, looked at a little bit hopefully. It stands for Virtual Machine Extension. And it's very complex. The documentation, it's ridiculous. If you read through this, I have no idea how I want to implement a simple VMM in this environment. They provide so much extended, cool functionality, all these access control lists, blah, blah, blah. They've extended page tables. It just makes it so much more complex. So the interesting thing here is the virtual machine monitor can allow or deny guests to specific registers, depending on how you set up access. So, for instance, Intel could release some code, VMware could release some code that uses the virtual extensions on Intel processors, and they implement something incorrectly, and they allow access to an MSR that they shouldn't, or something like that. This is, of course, just me speculating what could happen. I haven't actually implemented this yet. It's also interesting that the microcode responsible for reading from certain MSRs in the non-root VMM, it's different. So there's a specific MSR you're reading from. If it's let's say the sysenter MSRs, for instance, the EIP, the stack frame, all that stuff, the microcode will be different. So there might be bugs in some of this stuff that people don't actually use, given that some of the MSRs weren't checked by their quality assurance team. These are just random ideas I'm throwing out to you guys. This is just something I want you to think about if you guys actually do hack on this stuff. It's cool, complex virtual machine monitor code to look into. And obviously, I think in the future, the virtual machine breaking, like the cloudburst type of exploits, are going to become more relevant as most of our technology is virtualized. Most of our services will be running in some sort of virtual machine. So I think the virtual machine breaks will be very important in the future, if not now. Okay, so that's step one. I've given you guys a red pill. You have a way to detect in one instruction if you're running in a virtual machine. Now we're going to talk about tracing, some dynamic code analysis, running some code and tracing it. So a lot of people now use this fancy name, dynamic binary instrumentation, which is really awesome, actually. It's been around forever. So something like Valgrind or Valgrind, depending on how you say it, has been around for a long time. There's stuff like PIN. There's stuff like Dynamo Rio out there that you guys can use. It's all really cool stuff for debugging and performance, for optimizing your code. It's not so great if you're trying to run code that tries to be stealthy or tries to evade analysis, because it's obviously modifying the binary in some way, so that means that code could exist to check to see if the binary is modified, or the stack is not as it should be, because this dynamic framework has modified memory. So you could also patch the sample you're looking at to make sure it doesn't checksum itself or something like that. Like a lot of Skype stuff and Spotify, the music client, they do checking of memory, but this is complex and this takes time, and I'm lazy, so I don't want to have to do binary patching by hand, essentially. Luckily, Intel, through the MSRs we're going to talk about, provides something called last branch recording, which is not anything new. This is not something they just released today. This has been around since, there's code out there since 2006 that leverages this, but I'm going to hopefully tell you a novel way to do it that's very, very fast. And they also provide a lot more functionality through debugging and performance mechanisms that if you guys are interested in, you should read volume 3B of their the Intel x86 documentation. So we're using last branch reporting, and so that essentially means every jump, every exception, there's a few other cases where the processor, as it's executing code, will stop to check if you want to record when a branch is taken. So we can essentially leverage that functionality and record it. And there's a couple different ways you can do that. So they have a last branch recording stack, which means you have a small amount of space available. I think it's 7 slots. So it's essentially a cyclical buffer of 7 slots that overwrite each other. So you'll have a very limited window of memory to review. So you have the LBR stack, which you could use. If you're only interested, like, let's say something crashed, you just want to see what happened recently, you use the LBR stack. Very easy to implement, very nice. There's something called track on branch, which essentially sets the track E flag, which will allow a program to take control of execution whenever a branch happens. This is really slow, and this is what things like Process Stalker that Pedro Ramini came out with use. It's really awesome. It works well. It allows you full disassembly, but it's really slow. And then there's something called the branch trace store, which is what we're going to use today. And it's essentially a log of branches taken. So it's really very fast in that when a branch is taken, it just writes down the linear address of where it was in memory, and then just continues on. So it's very, very fast. And you have options. You can use a cyclical buffer similar to the LBR stack, which is kind of lame, and you can do an interrupt. So every time your memory that you've given the processor to use gets full, it interrupts, so you can handle that situation and reset the pointer to allow it to log more data, which use the local advanced interrupt controller. I forget what that said, sorry. And then you have options to trace ring 0 or ring 3 or both. So for the stuff that I'm interested in, which is essentially malware, I only care about tracing the operating system. So it's very fast if you turn on trace only the OS. Or sorry, trace only, I'm only interested in userland stuff. I don't care about the OS. I don't care what the kernel is doing. I only care about userland stuff. So this is an MSR here. This is the MSR debug CTLA. And to set up these mechanisms I just described, you turn on these bits in the MSR and just write to it. So there's all these options here, very cool stuff, very fun to play with, very useful in debugging. And this is the debug store as you have to set up in memory. So yourself, it's kind of tough to do this with just documentation Intel provides, but you allocate a VX buffer management area, and you allocate the VTX buffer, and you tell it how much data you want to store. So we're interested in the entire execution of the program. From start to finish, I want to know every single branch that was taken. So you can set up all this stuff yourself, and this is just the format that you have to do, or else you'll bug check a Windows machine. And this is how it's stored in memory. You get the last branch from, the last branch to. And Intel's verbiage is linear address. But actually, after segmentation has been applied. So you actually get, in my opinion, virtual address, where it was actually executing in the context of the thread you're actually monitoring. So it's really fucking useful. And then you can also get, was the branch predicted, which we're still trying to see if we can use that of any use to us yet, but it's essentially wasting a ton of memory because we're allocating all that memory for each branch, and we get only using one bit of that. So my Windows implementation is called Miser at the bottom here. It's MSR Miser. It mimics malware. There's a userland component that drops a payload that detects if you're using PAE, physical address extensions, which is very similar. It's simple to do once you know what you're doing, but we didn't. So I'm just I'm using symbols to. It's stupid. Just gonna move on. I have a userland component. It talks to the kernel and gets data back and forth from it. This is the diagram here. For every CPU you have, you need to set the MSRs properly, and for every APIC you have, you need to set the local vector table if you're using interrupts to call your code. So my code hijacks swap context, which everybody does. It's nothing new, and then we record the traces and send them to userland. The code I have is now public for you guys. It's not up on GitHub because my computer crashed this morning. Catastrophic hardware failure, as almost happened again. So I will put this up tomorrow or the next day. It's really horrible code. I'm a horrible C++ developer, but it works. It's something to play with. It's something that you guys should look at. Tell me why it sucks, etc. The performance is actually really good. I'm going to just slide through this stuff. I use this sample application here, which is just essentially, it's very tough for the processor to optimize this code. It has to go through all of these conditions here. So we go through, so essentially you pass an argument, how many times you want to loop through, and then I'll print out how long it took to go through all those conditions. So the performance here, with only running through that loop once, native, unfortunately the resolution here is milliseconds, so it's tough to give you guys a good idea of the actual performance, but it's good enough. Native, it's 0 milliseconds. My code is 0 milliseconds. The Cozinc trace suite is 2,391 milliseconds. Int_count1, which uses PIN, which is dynamic instrumentation, is huge. PagerDump's process stalker is huge, and if you single step through the code, that's how long it takes. So these are huge performance tips. Then to get some better perspective, if you do 10,000 loops of that performance code I showed you, here's the performance. So you guys can review the slides later. I don't want to go through this stuff almost out of time. Post-processing, like what are you going to do? This gets into the analysis phase. What do you do with this data? You got all these basic blocks. You know which jumps were taken, which jumps were not taken. There's a lot of research in this area. I have some ideas just to show you guys. Here, we're doing heat maps. So the code that's called a lot, we light up in grayscale. We make it white. So here's a piece of malware, and this represents the entire memory space it was executing in. So obviously this doesn't make much sense. It looks like static. And then we run some filtering through it, and we get a little better idea of what it looked like. And then if we run similar samples, the idea is that we can match them based on what code was hot. Like this code here might be, socket or something, some socket operations or something like that. So that's the idea. It's just random. It's not actually being used yet at our company. I have a quick demo I want to show you guys. I'm just going to trace Skype. So Skype has a lot of anti-RE stuff built into it. So if you just attach a debugger to Skype using Windows, Skype will exit. So I'm just going to show you guys real quickly here the code that I wrote that actually works. So I'm going to start. The kernel driver is patching itself. It's detecting the offsets and patching. Not too cool. I'm going to run. Let's check. You can see I'm showing you the vectors and the memory addresses with all this cool shit. So I'm going to run Skype through the program here. You can see it's getting a ton of instructions. As you can imagine, if you run a giant program like Skype, it's going to be doing a lot of things to start up. So the performance is still pretty good. I can't actually log in here because I'm not connected to anything, but you can see that right now, trust me, I know this, the code now has checked to see if the debugger is attached or anybody's tracing it and will exit. And you can see performance is I. Show you this. The UI stuff works fast. So this is tracing Skype. And I can't show you the output, but it's got a ton of data here. So there you go, it's tracing stuff. So there's also some similar code people have done in the past. So there's a Linux implementation, if you guys use Linux, called ptrace BTS, done by Marcus Metzger of Intel. It's actually part of the, or it's actually not part of the Linux tree yet. There's a academic paper that's coming out called XTREC, essentially doing the same thing I just showed you in that demo, but using AMD by a guy called Amit Sudivan. Cool stuff. Pedro Mamini's process Docker, Chaplon branch, kind of slow. Malware can easily detect that. Saffron is ring 0 dynamic instrumentation using pin, so it takes pin into the kernel. It's kind of like it uses page faults to allow it to call back to its own code. And there's this cool thing called virtual machine introspection that everyone's talking about the past 5 years. That something called Azure, guys from Dembala do, but it's not open source. Extensions to the idea I've just shown you. Hopefully you guys are academics and you like to write papers or something. You could do full-fledged kernel debugging, leveraging branch tracing and PEBs. It's a possibility, very fast. As you can imagine, a lot of the jump to the same code. So our idea was to use Huffman compression of the branch trace store because it eats a ton of kernel memory of memory. So just compress it as it's actually logging it, and you can get the same data. Or the next idea is using compressibility of the recorded jumps to classify traces. So similar malware families might have the same compressibility, given that they call the same APIs over and over again. You can also use the code I have to enrich your IDBs in IDA. This is Julio's idea, somewhere around here. It's actually really valuable because you will know immediately what's code and what's not. There's a lot of plugins that are good already, but it's just, the code's already here. This next slide is a little more experimental stuff that I don't even know will work. Measuring the distance between basic blocks, using some machine learning to train on jump distance. So you have samples, they might have the same jump distance between similar sized basic blocks. It's just a complete batshit crazy idea. It might work, why not? And then clobbering memory strategically with the debug store. So if a non-root VMM is allowed to write to this MSR, it might be able to overwrite memory in a different VM. It's a possibility. To end the talk, I gotta do some greets to Josh, Sam, Zen, guys in social, and the guys in KOSEC. And that's it. If you guys have any questions, please talk to me now or after we hang out drinking. Thanks, community.
What was the meaning of the Amazon that you showed for your red pill? That Amazon, what is used origin? Where is any Amazon?
Can you repeat that?
Yeah, the Amazon register that you use it for the red pill.
Oh, for the red pill. Oh, sorry, that's the debug. That's just the debug CTLA MSR. So essentially, it's just the one I'm using to do all the other debug stuff. If you just actually try to read that MSR itself, it should fill out the bit field with all the things that are turned on and off. But if it's not supported in the VM, it will just give you all S, which won't work. So, yeah.
¿Alguna otra pregunta?
So the idea is, yes, you're right. The idea is those measure the distances. So the addresses in memory will fluctuate potentially, but if you measure the distances, they you're right. It might not work. I don't know. That's a good point. Obviously, the distances will be different if the basic blocks are different in memory. But the idea is the compiler will arrange, different compilers will arrange stuff differently. So the distances might be small because of some differences in memory alignment, but if a compiler puts a basic block way so far away, then a different compiler, you would be able to detect that. So while the distances and the addresses will fluctuate, you can use the distances still, hopefully, to classify similar compilers that were used. That might work. But good point.
So you needed to write a Windows driver in order to set the instruction, to give the instruction, is it?
Yeah. No, the only reason I needed a Windows driver was to hijack the swap context routine. You can actually do all the MSR setting from Userland in Windows if you have the right privileges.
¿Una pregunta?